All right, folks. In a previous video, I did the coax cylinder. We have a solid cylinder and a solid shell around it. And we wanted to compute the electric field in all four regions, here, 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 and outside. And we went through the derivation where we have constant charge density or a uniform charge density on the inside cylinder or inside the inside cylinder and the shell volume charge density. And we derived expressions for the electric field, and we justified, not worrying about the shells, the caps, and we came with this expression, which is a very important expression. This one is electric field a distance r away from the enclosed charge, or that surrounds a certain charge q. And again, this expression right now, the way it is, especially the 2 pi RL, this has to do with the Gaussian surface. This is a geometry part, because the Gaussian surface is an imaginary surface, right? Imaginary cylindrical surface, and we're only concerned with the surface of the cylinder, not the caps. The physical part is Q enclosed. Is how much Q is enclosed in each Gaussian surface of radius r and length L, as we shown last time. Okay, so that's where the physical amount of charge comes in. Again, in the previous video, I did this, where here I take the charge densities to be constant, rho zero. Again, charge density has units of coulombs per meter cube. Okay, so that's constant. But now I'd like to take non-uniform or constant charge densities. I want to compute the basically the electric field in the three regions. But our main focus will be Q enclosed, because we already have an expression for the electric field, right? So for part two, we have E, that's Q enclosed over 2 pi L r epsilon naught. I will always take a Gaussian cylinder surrounding either a shell or inside a shell, or whatever the geometry inside might be. If it's a straight line, it has to have cylindrical symmetry, right? It's not whatever. It has to have cylindrical symmetry. It could be an infinite line of charge. It could be a solid cylinder, a hollow cylinder like a conductor, or a hollow shell, a conductor, non-conducting cylinder, whatever. As long as the geometry is cylindrical, my Gaussian surface will be a cylinder of radius r, length L. And my job now is to compute this depending on the charge density. So let's take outside on the shell the charge density. We'll call it rho 1. Okay, we'll say rho 1. Let's call it rho A. Okay. And inside, we'll call it rho B r squared. Rho A and rho B are constants, and the units have to match such that this comes out coulomb per meter cube. So maybe this is like coulomb per meter to the 4, and this is coulomb per meter to the 5, so that at the end, rho 1 or rho 2 come out with coulomb per meter cube. So now, we'll go to this color. Let's do part A. When R is less than R1, I'm inside the cylinder, and inside that cylinder, my density is rho 2. So here's the cylinder, the inside one. Okay. Let me draw it like this. Here's R1. I make my Gaussian surface inside it of length L and little r for the radius. So now my electric field again is this. How much Q enclosed is inside this cylinder? Well, again, let's go back and we wrote before Q is rho times V, the density times the volume. That's if the density is uniform. And whether it is or not, the actual definition is like this. Integral of rho r dr d phi dz. This is the element volume in 3 dimensions, and here's rho. And these integrals one will be for r, one will be for phi, one will be for z. So it all depends on rho, whether it's a function of r, phi, or z. We manipulate this integral. Now, if rho is constant, rho comes out, and only if it's constant. And we'll have this triple integral of r dr d phi dz. And what is this? Just the volume of a cylinder. Okay? But in this case, rho is not constant. In this case, rho 2, I call it rho b r squared. Therefore, Q enclosed equals triple integral rho right here, which is rho br squared times r dr times d phi times dc. So as we can see, this is basically rho is radial, so it has no effect on phi and z. And the integral of phi and z and r are all independent, so I can rewrite this. And now we'll put the limits in. Except for r. And let me take the rho b out. It's constant. R cubed dr. So z goes along the axis of the cylinder. That goes from 0 to L. Phi goes around the cylinder, 0 to 2 pi. R cubed, I'm going from 0 to r, because I'm going from the origin all the way to the edge of the white cylinder. Now, the first two give me L times 2 pi. And this is the only time I will show these explicitly, because the densities I gave you are all radial. They have no phi or z dependence. So we're always, and every time we compute Q enclosed, we're going to separate the integrals like this, and we're always going to get 2 pi L out. So there's no need to do it. We're just going to assume that that's the case. So here we'll have 2 pi L rho b integral from 0 to r cubed dr. That's 2 pi L rho b times, this is r to the 4 over 4. Even after you plug the limits, it's going to be r to the 4 over 4. And this is the charge enclosed inside my cylinder, okay? So the electric field inside that cylinder is going to be Q enclosed divided by 2 pi L r epsilon naught. 2 pi L cancels 2 pi L. Rho b is sitting over here. R to the 4 over r will give me an r cubed. This 4 drops down, combines with the epsilon naught. And this is my electric field. Again, it's radial for r less than r1. And the electric field is radial. So in general, we can write this. And again, I want to only write it once because all our electric fields here are radial. of 4 epsilon naught. R hat. There it is. Part B. Here's my cylinder, the inside cylinder. Radius R1. My Gaussian surface, I have to take it right here. Of radius R, such that R is between R1 and the shell. All right. Again, how much charge is enclosed in this white surface, white cylindrical Gaussian surface? Well, this basically encircles the whole cylinder. So basically, whatever charge on the cylinder, the total charge of the cylinder is, that's how much is enclosed. Now, I have to remember there is no charge between in this region right here. Okay, it's just empty space. The only charge distribution that we have is from 0 to R1. So now my charge Q enclosed is what? Again, we said in this case, I'm going to take these three out. We're still reading, working with row 2 because we're talking about the inside cylinder. So it's going to be rho B 2 pi L. And I'm going to have here the integral of R cubed dr from 0 to R1. Okay. I can only integrate the density up to the edge of the cylinder. I cannot go beyond that. So this will be 2 pi L rho 0 R rho B, sorry, not rho 0. Two pi L rho B, R to the 4 over 4 from 0 to R1. So that's going to be 2 pi L rho B, R1 to the 4 over 4. So the electric field, again, I'll just write the magnitude, is Q enclosed, R1 to the 4 over 4 over 2 pi L R epsilon naught. 2 pi L cancel, rho 0, rho B, R1 to the 4 on top over, this 4 goes down, there's an R and epsilon naught left. R is between R1 and R2. Here the electric field again goes as 1 over R. And remember, the units of rho B will take care of things, right? Rho B has the proper units so that the electric field comes out to be the proper units. Okay? So that was part B. Part C. Let's draw part C here. Okay. So for part C, here's what I have. R3, R2, R1. This is a cross section of the cylinders of the coax. So here's R1, here's R2, here's R3. And now I choose my Gaussian surface inside the shell because part C is R is between R2 and R3. So this is little r. So now, let's choose this. Let's make it big. So this is the contribution from the shell. Because remember, I'm still looking for Q enclosed. I already have the expression for the electric field. The expression I have depends on a Gaussian surface of radius r, length L. The only difference between all these situations is how much charge is enclosed inside that Gaussian surface. So at first look, obviously, it's everything below little r. But when we investigate it a little closer, we only have this little band right here between R2 and little r. So right here. And we have the whole cylinder inside it. So the total charge, I'm going to call this band. So the total charge, Q enclosed, is Q band plus Q cylinder. Well, how much charge is enclosed in the cylinder? I just computed this right here. So I already know this. I just need the Q and the band. And now I have to use rho 1 because rho 1 is the density in the shell, and that's rho AR. Okay, so this is all good. So now Q band equals 2 pi L. That's from the integral of pi of phi and z, or phi and z. And then I have an integral for R, integral for rho rho 1 r dr. Well, rho 1 is rho A r. So rho A goes out, 2 pi L rho A, integral of R times r dr. This r is from the density. So it's going to give me an r squared. What are my limits of integration? I'm only adding the contributions between R2 and little r. That's it in this little band. Those contributions along that radius only from R2 to R have that density, rho AR. So now this is R squared, so it's going to be R cubed over 3. So 2 pi L rho A, R cubed over 3 from R2 to R. So I'll have 2 pi L rho A over 3 R cubed minus R2 cubed. That is the Q band. Q enclosed total is Q band plus Q cylinder, which is 2 pi L rho B times R 1 to the 4 over 4. All right. Do not get confused again that here we have an R cubed, here we have an R to the 4. This density is proper units to give us the correct total charge density, right? This is the constant. And thus will give us the correct Q enclosed in coulombs, and then will give us the correct electric field. So now E in that region is this charge enclosed, 2 pi L rho A over 3 R cubed minus R2 cubed plus 2 pi L rho B R1 to the 4 over 4 over 2 pi L R epsilon naught. This cancels this, cancels this. I have a 3 and a 4. So we can combine them. And I'm not going to simplify the top. Just going to keep it. So basically we'll have 4 rho A r cubed minus r2 cubed plus 3 rho B r1 to the 4 over 12. I got a common denominator between the 3 and the 4, 12. That's why I have a 4 here and a 3 there. R epsilon naught. And that is the electric field. For R between R2 and R3. Okay. Last one. Again, and my Gaussian surface is out here. So the Gaussian surface has R. That's R1. That's R2. And this is R3. So now, Q enclosed is the whole shell. All right. Plus the cylinder. We already know what Q enclosed is here, because right now this white Gaussian surface encloses the shell and encloses the cylinder. So all we gotta do is compute Q shell. Let's go up a little bit here. And let's look how we computed the band right there. What is the difference between computing Q for this band and computing Q for the shell? In other words, this area right here. Do it in a different color. How do I compute the total charge in that shell, knowing that I computed the charge for the band? But again, I want to only count the charges that contribute, or the area or the geometry that contributes to the total charge. When I was computing the band, I went from the edge of the shell down here to where my Gaussian surface is. But right now, since my Gaussian surface is outside the shell, I can only go to the edge of the shell. I cannot go beyond it. So basically, these limits of integration right here, this one becomes R3 when I'm computing it for the band, for the shell. So the only difference is this, instead of being R cubed, it'll become R3 cubed. That's all. So for that, again, this is equal to 2 pi L rho A over 3 R3 cubed minus R2 cubed. That's it. That's Q enclosed for the shell. And then for the cylinder now, 2 pi L rho B over R1 to the 4 over 4. So the electric field will be exactly the same as this one, but instead of R cubed here, not this, just this one, I'll have R3 cubed. So I'll have 4 rho A R3 cubed minus R2 cubed plus 3 rho B R1 to the 4 over 12 R epsilon naught. Again, it's radial. That's when I'm outside All right, so the next video that I'll do is probably an infinite line of charge using Gauss's law and using Coulomb's law. Compute the electric field at distance x or whatever away, and then go to an infinite surface, which we did already when we did the cylinder, when we did the disk. You take the disk and you let R go to infinity in the disk. When you let R go to infinity, now you got an infinite sheet, basically, of charge. And we want to compute the electric field right above it. Okay? We'll do it Coulomb's law, then we'll go back, do it Gauss's law. All right? Then after these, we'll probably do some point charges again, just to add and subtract factors. And then we'll start videos on potential difference. All right. I hope this was helpful. And I'll see you in the next video. Thank you.